Swayam Prabha. Digital India. Educated India.
So in this lecture, I'll be talking about adsorption and how to model an adsorption process through stochastic framework. As a chemical engineer, adsorption is a very important mass transfer operation. Adsorption involves typically a transfer of a molecule from a gas or from a liquid into a solid substrate. Okay, and this adsorption leads to several separation possibilities. Like if you want to remove a dye or a pollutant from a effluent, you can use adsorption, or if you want to remove some pollutants from the air. So you can do also carbon dioxide capture, any pollutant gases you can remove. So adsorption is a very classical separation process for chemical engineer. Okay, and then one of the key thing in this case is to find the right adsorbent. Okay, adsorbent here is the substrate, the solid substrate on to which the molecules will adsorb. If you ever bought any goods from Amazon, it comes with a package and you see a small sachet in the package. So that will have small particles, those are silica gel, and the reason why we have that is because it want to absorbs moisture in the package. Okay, especially if you are buying some electronic goods, you always see that silica gel packet inside the cap. That's because to kind of absorb any moisture present in the packaging. Okay, so silica, zeolite, activated carbon, metal organic frameworks, there are so much of interest in the context of developing new kinds of adsorbent material. So we all realize that adsorption is a very important process. Development of new adsorbent is always an active research area. Now from a theoretical perspective, we would like to build some models so that we can make sense of these experimental data, that when I change certain parameters experimentally, how the amount of molecules that are adsorbed is varied. Okay, so in that context, there are several adsorption models. There is this BET adsorption isotherm, there is Langmuir adsorption isotherm, Freundlich, Tumkin, and so on. Okay, as a chemical engineer in mass transfer, you could have studied many such adsorption processes. So first what I want to do is, I will describe a deterministic approach of solving this adsorption problem in a very simple setting, and then later on we will try to do that through a stochastic approach. Okay, so what we will consider is Langmuir adsorption. So here let's say you have a solid substrate. So you can imagine that there are lattice points on which a gas molecule can sit or adsorb. Okay, so we call this is an adsorbent, and this adsorbent is exposed to a gas. Okay, and this gas contains certain molecule solute that will adsorb to this surface specifically. Okay, so there could be inert background. Okay, for example, you have air and then you have water as a solute, and water may want to adsorb to the surface. Okay, so you have a gas, and then we may say that the partial pressure of the solute is some Pa. Okay, and temperature is some T. So usually adsorption experiments are held at constant temperature. That's why we call them as adsorption isotherms. Okay, constant temperature, the partial pressure of the solute is given, and then you have a particular surface area for the adsorbent. Okay, so we say surface area or we say number of active sites, they are all equivalent terms. And what we want to know is, for a given temperature and given adsorbent material, if I change the partial pressure of this gas, how much I can adsorb into this. Okay, so that's the question we are asking. The way we do that is, you have a gas molecule A and it sits onto a lattice on a solid substrate, and then you have an adsorbed molecule. The adsorbed molecule can be represented as A star. This A means a free molecule in the gas space. It finds a particular site S, okay, and then when it adsorbs here, we call them as an adsorption. So the forward reaction is an adsorption, but it is not an irreversible adsorption. An adsorbed molecule can also, because of thermal fluctuation, can also evaporate back. That we call it as a desorption. When an adsorbed molecule leaves, it brings a new free molecule and it also opens up the site so that new molecule can also come and adsorb. Okay, it's just like how you're sitting, how you're occupying the seats. Empty seats are vacant sites, the filled ones are adsorbed sites. You can come and sit and you can leave. Okay, so kind of similar kind of a process is happening in this case. So our aim, as I said before, is I want to find out how many molecules are adsorbed, okay, when I change this partial pressure of the gas. Okay, so that's a question we want to answer. And there is a kinetic part to it, and as well as there is an equilibrium part to it. Okay, so right now in the deterministic approach, we are often interested in the thermodynamic aspect. At equilibrium, when the system reaches equilibrium, what is the equilibrium occupancy of this substrate? That's what we want to ask. So our approach is to write an equation, the rate equation for the rate of change of the concentration of the adsorbed as a function of time, is to set up a ODE. So here you see that this is equal to, we say the forward reaction is adsorption. So Ka is the adsorption rate constant and is proportional to the concentration of these two. The concentration of A in the gas phase we say as Pa, and the concentration of this vacant site is S. So this is a forward reaction. Okay, through this forward reaction, more and more adsorbed molecules are created, and the reverse is to look at the desorption, where we say a different constant Kd, d meaning desorption, and the rate is proportional to how many number of adsorbed molecules are present at that particular time. Okay, so we are going to say this is A star. So if you want to solve this equation, you can solve this and then get time evolution of A star as a function of time, and for that you need Ka and Kd, and you also need how the number of free sites are changing with respect to time. To do this, to get this S, what you can do is you can write the total number of sites minus the number of occupied sites. The number of occupied site is nothing but A star, because each molecule occupies one site. Okay, so basically like how we write the number balance in the kind of A to B reversible reaction, where the number is conserved. So here the number of sites are conserved. The total sites can either be free or it can be occupied. So the sum of occupied and free sites should be constant. It's a conserved quantity. So through this expression, I can find what S is. Okay, so with this equation, I can replace S, write everything in terms of A star. So I have only one variable, and all the constant Ka, Kd, if that is known, you can integrate this, and then you can find how the number of molecules of A varies with the time for a given set of Ka, Pa and Kd. The temperature enters in the constants Ka and Kd. If you change the temperature, Ka and Kd will change. Pa is more like an experimental control. You can decide what partial pressure you want this experiment to be. So from here onwards, it's a solution of a simple one ODE. You get an analytical equation and you can show how as a function of time. So it will exponentially increase to a equilibrium value. But if you're not interested in the kinetics, you're looking at only the equilibrium, the final equilibrium value, you can set this equal to 0 and you can derive the condition for equilibrium. Okay, so at equilibrium, the rate of change of adsorbed molecule concentration is 0. So that means Ka/Pa So I'm equating this to this, and this S is now written as total number of sites minus the concentration of adsorbed ones. that should be equal to KD A. And we say this is at equilibrium. So, this is equilibrium. So, now you can solve for A star. So, A star at equilibrium is equal to Ka Pa plus Kd So, there is a star term here and there is another A star term here, and you bring all of them in one direction, one side. So, you will have A star equilibrium times sum of Kd plus Kapa, and the other term goes to the other side. So, we can solve A star at equilibrium is basically Ka Pa S naught by Kpa plus Kd. Now, what we can do, we can actually define an equilibrium constant K as Ka by Kd. So, if you take Kd out, you will get capital K Pa by 1 plus Kpa, and then you can bring this S naught here, and then we call this as the coverage. The equilibrium coverage of the substrate or adsorbent is given as equilibrium constant K, which is constant for a given temperature, times Pa 1 plus Kpa. Okay. So, this function, if you plot as a function of Pa, you see that when the Pa is very small, okay, for a given K value, when Pa is very small, you will see that this term is much more than this. So, this is actually negligible. So, you will see that Kpa, that is proportional to Pa. So, you will see that at a very low Pa, it is increasing proportional to Pa, okay, where the slope here is rate constant K. But then when Ka increases very high, okay, when Ka becomes very large, what happens is that this term actually is much more compared to this. You will see that it basically reaches 1, okay. So, you will probably reach 1. So, in reality you will see something like this, okay. So, in fact, when you do an experiment like this, okay, what you will do is you will conduct several set of experiments. In one experiment, you will change the pressure Pa, partial pressure, and look at the system to reach equilibrium, and through some characterization you measure how many molecules are adsorbed on the surface, and based on that you will get the coverage, and you would see some points like this. So, it nicely follows this kind of an adsorption isotherm, okay. So, whenever you see an experiment data going like this, initially linear and then saturating, it is an indication of a Langmuir adsorption, okay, and this is the adsorption equation that we use. This is a very idealized model because it assumes several things. It assumes that all the sites on the adsorbent are equally likely in terms of its energetic, okay. Every site is having same energetic, so molecule does not really prefer one site over the other, okay. So, adsorption rate depends only on the number of vacant site, not necessarily where the site is, okay, because each sites are identical. But in reality that may not be true. Some sites are more energetic, some sites are not very more energetic. So, there is also some sort of variation in the adsorption capacity of the site. And another thing is, we say that one site occupied by only one molecule, but many times that is not the case. One molecule may actually occupy 2 or more sites also, okay. So, here we are assuming 1-to-1 stoichiometry, one site, one molecule, Okay, but in reality, one molecule may take several sites, or sometimes several molecules also can sit on one single site. So those are experimental variations. And many times adsorption can also lead to multi-layer adsorption. So first adsorption happens on a monolayer, and further more and more molecule can adsorb on the preformed monolayer, and you get what is called this multi-layer. Okay, so those are more physically realistic situations. But languid adsorption on the other hand has a very simple model that the sites are equivalent, one molecule per site, only monolayer is possible, and so on. And no interaction between the molecules that are adsorbed. So it doesn't affect the free incoming molecule to the site. So under those assumptions, you will see this kind of behavior. And this K here, as I said, is something can be obtained from equilibrium thermodynamics. You say minus RT ln K is equal to delta G adsorption. If I know what is the delta G, that is the free energy change for adsorption, you can get that K from here, okay, and that K goes in here. For a given temperature T, K is uniquely found, and that's what goes in here. So this is how we have been conventionally deterministically handling adsorption problems, okay, adsorption and adsorption models. So now what we want to do is look at the same problem, but more from a stochastic perspective, okay. So that means we are going to look at chemical master equation. We are going to look at the adsorption as a process where the molecule can adsorb and desorb in a stepwise fashion, and then write the chemical master equation and then solve it. And we will see that the predictions of the coverage is basically the mean value of the coverage, and we can also get what is the fluctuation about this mean through stochastic approach. But this approach does not give you what is the likelihood of the fluctuation, okay. This does not tell me whether I am looking at a size of 1 meter square adsorption area, or I am talking about 1 nanometer square adsorption area. It will give the same prediction. It does not incorporate any stochastic or any randomness in the problem, especially when you go to smaller size, okay. So let us look at the stochastic approach to this problem. Okay, so this is our reaction model for adsorption. Let n is Na star. This is nothing but the number of adsorbed molecule. And we treat this as a stochastic variable. S naught is the total number of sites, total number of sites. So we write the rate of change of n using master equation. So if you look at this this problem, we have two reaction channels, adsorption and then desorption. In the adsorption, you are looking at what are the events that will affect state n. Okay, so when the state is at n, and any adsorption can take the system to n plus 1. Okay, because adsorption means adding one molecule to the adsorbed site. Okay, so here in this context, m is n plus 1. Or if the state is at m minus 1, one adsorption can lead to creation of site n. So here m is n minus 1. Okay, so m basically means what states bring to state n. Okay, so here a state of n plus 1 brings to n, and here another state of n minus 1 is bringing to state n. So we have found two possible m values for adsorption alone. Similarly, if you look at desorption, desorption means a molecule is removed from the surface to the gas phase. When the system is at n, one desorption can lead to n minus 1, or when the state is at n plus 1, one desorption can lead to n. Both of these events affect the state of n by creating or by destroying it. So we have to take care of all these four events. So what I am going to do is I am going to write m value, these two and these two, but these are two different things. This is an adsorption with the different rate constants, and this is a desorption with the two different rate constants. Okay, so let's substitute for m is equal to 1 plus 1 n minus 1 and write this up. So these terms are for adsorption, and these are for desorption. So now we have to see which of these terms are going to survive and what gets eliminated. So if you look at this one, so this entire term on the first line here is for adsorption. Is it possible that a system at n plus 1 going to n by adsorption? Currently I am at n plus 1, and adsorption event happens. Can this lead to n plus n? Can we go from n plus 1 to n by adsorption? That's not possible, because adsorption means increasing n. So by this term actually is 0. Okay, this actually is not permitted. Is it possible that system at n, one adsorption happens and then the system goes to n plus 1? Is it allowed? Can we go from n to n plus 1 by adsorption? Yes, right? So this is actually a finite quantity. So dp by dt, and what would this be? How do we write this rate? W n n plus 1, the rate of adsorption being at n. So rate constant is Ka, right, and Pa, and number of vacant sites, right? The adsorption is proportional to number of vacant sites. What is the number of vacant sites when there is already n occupied sites. S naught minus n. Okay, good. S naught minus n. So this is going to be the rate for this. Adsorption rate constant times the partial pressure of the gas times the number of free sites. That tells you the rate of adsorption, where the system will go from n to n plus 1 times the probability that the system is at n at time t. So we have handled this. What about this? Can we have a system at n minus 1 and adsorption even happens and then lead to n? Is it allowed? Yeah. There's going to be minus. Yes. Yes, you are right. There has to be minus. Yes. System is at n minus 1, adsorption happens and goes from n minus 1 to n. Is it permissible? Permissible. What about the rates? So adsorption, so Ka, Pa, and I need the number of sites when the occupied sites are n minus 1. Okay. So this is going to be S naught minus n plus 1 times P of n minus 1 comma t. Okay. So this is taken care of. Now again we are saying I am at state n and adsorption happens. Can I go to state n minus 1? That's not permissible. So that has also go to 0. So now we have handled two terms for the adsorption. We are asking the same question about desorption. So here state is at n plus 1, a desorption happens and you want to go to state n. Permissible? Yeah? Okay. So here we have Kd, that is a desorption rate constant, times the number of occupied sites, that would be just n plus 1. What about this? You are at n, you are going to n plus 1 by desorption. Is it possible? You cannot go by increasing n by desorption, so this is not permissible. N minus 1 to n by desorption. From n minus 1 by desorption, you can only go to n minus 2, not n. Okay, so this also cancels. At n, you can definitely go to n minus 1 by desorption. So you have minus Kd the number of sites there is n and P of n. So this is what you will get for does this equation looks familiar to you? Have you seen this before? This form? Where? In a reversible reaction system, A going to be reversibly, if you look at the chemical master equation, we had exactly the same form. If you look at the prefactors, the rate constants, only that changes. Okay. So why I am invoking that, because we already saw how to derive the analytical solution for that. By simply changing the terms, we can directly write the solution for this. Okay, so that's the idea. So if you see the Ka Pa should be actually equal to Kf in the reactions problem, in the reversible reaction problem, and I think Kd is actually equivalent to Kb, the backward reaction rate constant, and n here meant Na in the reaction A to B. Okay, so all this right hand side was written for a chemical reaction going A to B reversibly. So if I replace all these terms by this, you would have got the chemical master equation derived for reversible reactions. Okay, so therefore we can directly write the equations for this. So in this problem, n refers to the number of adsorbed molecule. That's a random variable. If you look at the mean, so you solve this and then from there you can get mean and standard deviation. The mean of that n, okay, this Na star is the mean value of the small n here, and that is found to change with the time t via this equation, okay. And you have this exponent kt. This k is nothing but the addition of the two constants, kd plus kapa. And if you are interested in the equilibrium value that you can obtain by setting time t tending to infinity in this equation, okay. So then this term will vanish. So you will have S naught kapa by kd plus kapa. This is at equilibrium. And then if you introduce capital K as small ka by kd and theta as the equilibrium of adsorbed molecule versus the total number of sites, then you can show that theta is equal to kpa by 1 plus kpa. So as far as the mean is concerned, we are getting exactly the same result that we found from deterministic approach at equilibrium coverage. And this is a mean value. It's a mean coverage. And then you can also get a standard deviation. The standard deviation of this problem will also change with respect to Pa by this term. So the mean changes with Pa by this, and this is exactly like the deterministic approach, but you can also find what is the uncertainty about this mean depending upon this, based on this equation, okay. For every Pa you can calculate what is the error bar, what is the fluctuation about it, okay, what's the uncertainty about this. This extra information about the fluctuation about the mean is not obtained from the deterministic approach, but from this stochastic approach you can get that extra information, okay. So that's the main takeaway or the main key information that we obtain by doing this problem stochastically. Sorry? Yes. This is the equilibrium value. Yeah. In the class notes, I have given a reference. It's a review paper. If you go through that paper, you will see that the stochastic framework has been applied to many other complicated adsorption processes, okay, and many such realistic adsorption processes are not solvable analytically like this, okay. We have an analytical solution for very simple cases like this. In the case of this more sophisticated or more complex adsorption networks, we have to do numerically, okay. So right now I am focusing only on the analytical solutions. When we deal with the kinetic Monte Carlo simulation or the simulation, the numerical approach, we will revisit these problems again, and then whatever complex adsorption networks or complex reaction networks we have to resort to the simulation techniques. Okay, so the later part of the course, I'll be talking about various numerical algorithms to solve those problems which are complex, which are more sophisticated, that cannot avail any analytical solutions. Okay, but right now I think you should be comfortable with simple problems for which you should be able to write the master equation and you should be able to get analytical solution first hand. Okay, but if you want to do a project or research, this is not sufficient. Okay, this is very elementary, but this is important to know so that you can do far more complex or far more experimentally realistic problem in the project later on. Okay, so please pay attention to the derivation, look at what information we are doing and how is it related to the stochastic, related to the deterministic approach that we are looking at. So if you look at all the lectures that I have been doing, typically I start with a problem that is interesting to chemical engineers and then pose the problem from a deterministic approach, the conventional approach, what we get, what information we get, and then complement that with the stochastic approach and see what additional information we can bring in and how those are experimentally relevant. Okay, so if time permits, I would do a lot of case studies and a lot of experimental validation of the stochastic process. It all depends on how much time we have. Okay, so I'm hoping that I'll try to bring more and more chemical engineering relevant problems as we go along. Okay, so and you also have to follow the class notes and if you really want to do a good project on this course. Okay, so you have to do a lot of homework on this. So more information about this derivation solutions are available in the class notes for you to go through.